All right. So in the last lecture, we talked about the district training can be done on either model pair reason or data pair reason, right? So those are the two mainstream if you want to train a model across a machine or across computing devices like GPU. Okay. And we said that the model pair reason usually supported directly by the framework. He will when he try to dispatch or schedule your tasks to different computing devices, and it's often used on a single node while you have shared memory, so you don't need to actually copy the data between those computing devices. Okay. However, if you want to train your model across multiple machines without shared memory, then usually people use data pair reason because it doesn't need to change your code, and you simply copy the whole model on every machine and simply partition your data sets scattered around the machines. So each machine just train their local data set locally, independently, but they will swap the parameters, exchange the result of your forward propagation. uh, then they can derive or compute the gradient, the gradient across all the machines, and then broadcast the result to all the machine, and then uh, that then to do the backward propagation independently again. Okay. Um, so for with data pair reason, um, basically you just need to add a communication layer right across machines and try to uh, compute the gradients across machines. So that is what we call the parameter swapping. Okay. So of course, in general, we will use both pair reason at the same time. Depends on the situation, and many frameworks implement for for both of them. And you can use configuration to decide how you would like to parallelize the computation for your training, for your forward or backward propagation. Okay? So for this lecture, we will only focus on data pair reason because model pair reason involve not only communication but computation because you need to partition your computation into those tasks, right? But for data pair reason, we don't need to change anything about the computation. All we need is, as I said, to add the communication at the end of the forward propagation. So in order to provide efficient communication, there are different strategies to do parameter swapping. Okay, and the communication method can basically classified into either what we call the parameter server solution or the all reduced solution. Basically, parameter server solution is a centralized solution. Means that you will have a server that take control all the parameters, right? The weight of the model. Okay. So after the forward propagation, the worker will send the weight, right? After the forward propagation, you will depend on you will compute the loss, and then you will propagate this information to the parameter server. And so the delta W is your gradient, basically. Okay. So you will send the gradient to the parameter server, and the parameter server will collect the gradient from all the workers, and then take the average, as we said, right? In order to update the weight, and then the parameter server will broadcast the weight back to all the workers, so they can use the same weight to update their local models. Okay. So this is a centralized strategy, right? So we all know the problem for a centralized strategy. is that the parameter server can easily become the bottleneck. Not just because of the computation, but more importantly is the network bandwidth, right? If especially if you have multiple workers or more amount of number of workers, then all the workers need to send their network traffic to the server. So the server can easily become the bottleneck in this computation. Okay. So how can we? But however, there's a way to mitigate this problem by simply using multiple machines to act like the parameter server instead of just having one machine. And the reason you can use a multiple machine easily is because the weight update, right, on each weight or parameter is independently, right? They are completely independent to each other, right? Because every weight is follow this to update, right? Follow the gradient of its weight to update its result. So the update operation is actually completely independent across every parameter. So that means, for example, if you have maybe, in this case, maybe 14 parameters, then you can have 7 parameter servers, and that each parameter server to handle 2 parameter only. Okay, so it depends on which parameter you want to update. You will propagate the information to the corresponding server of that parameter. Okay, actually you can have any number of parameter server to spread out the load. Okay, however, it's not trivial how many parameter servers to use, because if you have too many parameter servers, you can see that we have to send out more number of messages, right? Because this is every worker need to send the update to each server. So if you have more servers, then for the worker, he also need to send out more messages, communicate to more number of servers. So um, in some way, it will increase the number of network requests in our system. Okay, and also we all know for networking, if the data size is larger, then the bandwidth utilization will be better, right? So if you spread this too much, then the amount of data you send to each server will reduce, and also reduce the transfer efficiency. Okay, so the number of parameter server is actually a magic number, right? If too low, you will have congestion. But if too large, then you might suffer from inefficient network transfer. Okay, so it's actually a tuning parameter for this strategy. Okay, so actually today people more like to use O-reduce strategy. Okay, so O-reduce is a peer-to-peer, fully distributed communication. Because you can see the way to do this or reduce is that every worker will send its weight to the you can use a ring. Basically, there's a many way to implement it, but the most efficient way, most commonly way to implement this is called the ring or reduce. So it will basically connect all the workers in a ring, and there's no server. Okay, unlike parameter server, we have dedicated server to manage parameters. But for all reduced solution, we only have worker. So that's another benefit for all reduced strategy. He doesn't need to have a dedicated process or server for this communication. Okay, and so every worker will simply just pass his weight to his right hand side, and you will, as you can imagine, we have we will show the figure later on. But basically, the message will forward uh, through this ring, and then after you circle around, that also means every worker receive your weight. So it's a kind of like broadcast, but The broadcast is not scalable because it's one-to-many relationship. But with a ring, it's you can see every worker only need to communicate with two other servers. No matter how many servers or how many workers are there, you only need to communicate uh, your neighbors on the right hand side and the left hand side. Okay, so at the end, more importantly, is this pattern can fully utilize the network bandwidth between those workers or machines, right? So if you have a fully connected network topology in your system, this strategy can utilize more links than the parameter server solution. Okay, so that's why you can balance the communication load. Okay, so you can prevent hotspot, and so at the end, because there's no network congestion, so it's possible it can achieve even better performance. Okay. However, the downside for all reduce is it can only support synchronous communication. Means that this all reduce operation needs to be performed like we know it's a collective code, right? So collective code means that if there's one worker that's somehow delay or not response, then we cannot complete this all reduce operation. On the other hand, for private server, the biggest advantage for private server is it can support asynchronous communication. As we will also mention later, there's the gradient descent algorithm based on asynchronous communication is what we call the asynchronous SGD, or sometimes we say it's a downpour SGD. Okay, and what it means is that you can see every worker they can communicate with parameter server independently. So if we relax the mathematic definition over here, we can every time we receive a delta, a gradient, we can we can update the weight immediately without waiting for others, right? We can divide the impact by the number of workers, right? So we can calculate this or update this in an incremental manner. So therefore, those workers does not require to propagate their weight at the same time. So that's why we can have an asynchronous communication for the distributed training. So if your environment and if your computing power for the workers are more diverse or they are heterogeneous, then parameter server will be the better solution. Okay, but if you are in a high performance system, usually with homogeneous computing nodes with equal computing power and fully connected network topology or well connected network topology, then all reduce will provide better performance. Okay. All right. So those are the two communication methods to enable or to realize distributed training, and usually they are both supported by the deep learning framework. Okay. All right. So the choice of communication method definitely matter. That's matter the most. But besides that, there are many other strategies to minimize communication overhead in distributed training. So we will show you a couple of strategies, just that you have an idea. And many of them already implemented in the framework you are using today. Okay, so I think it will be better and it will be useful for you to know the existing of those strategy, and sometimes you might even need to tune those strategy in order to achieve the best performance in your computing system. Okay. All right. So the first strategy related to distributed training or parallel training is the mini batch strategy. Okay. So actually, this strategy even work for a single server because, as we all know, most of the time we train our model on GPU, and GPU itself we know is a data parallelism processor, right? So in order to achieve the best performance, usually we want to have enough data parallelism in our computation, so we can fully utilize the GPU cores. So one way to do that is through the batch size. So I think many of you, if you have trained a model, you know there's an important hyperparameter called the batch size. That means how much records you want to train at the same time, right? And so basically what happened is, saying you have a data set with n data records, and then the batch size will partition the data set, right, by the size of your batch. So you will have several batch. And for GPU, it can basically compute one batch at a time. So that is what we call the mini batch SGD. Okay. All right. So so the reason we want to have this batch, because obviously if we have, for example, m records in one batch, then that means we can use m core to, right, evaluate the batch at the same time on GPU. Okay? Because every image or every record will be computed in parallel independently on GPU. Okay, so we usually want to increase the batch size to increase our hardware efficiency, right? So if we have a larger batch size, usually we can increase the hardware efficiency to fully utilize the GPU, okay? Because we have more our degree of parallelism will be increased. However, the downside for batching is that supposedly, originally, according to the math, you can see that we should evaluate one record at a time, right? Every time we evaluate one training data, we should update the weight before we start training for the next record. So, so that's the original form. But now, because we have the batch, so you can see over here, we will, for example, pass 10 records at a time. So the weight is just like distributed training. We only take the average of all the weight or all the gradient to update the weight. So actually, it will smooth out the impact, right, from each data point. So the result is that because it's more smooth, so sometimes it will more easily fall into some local optimal, or it will ignore the impact of certain data, right? Because it's smoothed it out. So as a result, if the batch size is too large, then maybe you will need to train longer, and you will overlook the impact of individual data. So that's why if the batch size is larger, usually your optimization efficiency will decrease, which means you probably need to train more iterations. You have to run for more epochs or go through those data set more runs. Okay, so it's a trade-off. You can process the data faster, but you have to process the data more number of iterations. Okay, so it's actually a trade-off. Okay. So again, the batch size, if it's too large or too small, will probably prolong your overall time to reach a certain target accuracy. Okay, but in reality, unfortunately, for GPU, we don't have that many memory, as we know. So usually the batch size never large enough. Okay, so because it's bounded by the GPU memory size. So at least for today, usually the principle is try to use the batch size as large as possible. But you should aware that it may not always give you the best overall training time if you just increase the batch size unlimitedly. Okay. All right, because still there's a trade-off exist. Okay. All right, so that's the first basic strategy. We have seen this very often, especially if we try to train our model on multiple cores or on GPU. Okay. The second strategy, also very often seen in distributed training, is the asynchronous SGD or downpool SGD, as I mentioned. Okay. And the idea is, like I said, basically for parameter server, it's not required to, you don't necessarily to have a barrier to to do the computation before you receive all the gradients. Okay, because you could also try to update the gradient, update the weight immediately after you receive a gradient from a single worker. Okay. However, again, because it's an asynchronous communication, so you won't suffer from the synchronization overhead, right? So you don't need to wait for other worker. But again, from the optimization point of view or the algorithm point of view, it's actually relax. You actually relax the computation. So the state for you to update the weight can become inconsistent between the model. And the reason is because if you can recall, in the data pair reason, when we talk about the synchronous SGD, we will ensure that all the models on all the machines are exactly the same. Because they receive the same weight, right, at the same time. But in asynchronous SGD, you can see the weight is always changing. So there will be a differences between those model weight. Okay, so the differences will depending on the delay, right, between those workers. So if the delay is longer, then the inconsistency between those local model will become more. So certainly that will affect your training results as well, right? Because there are more inaccuracy in the training process. Okay, but on the other hand, if there's more delay, you use asynchronous communication, then you can avoid more synchronization delay. So the performance will be improvement from the performance will be even more. So again, it's a trade-off between the performance and the training accuracy. So if at the end your goal is to reach certain accuracy, the degree of asynchronous should also be tuned. Okay. So how to tune the consistency? Um, so because of that problem, so today most deep learning framework support slow synchronous. They are not asynchronous because asynchronous is it doesn't restrict your delay, so your inconsistency will probably unbounded. But in order to bound this inconsistency, we have store synchronous strategy. So the idea of this strategy is you will keep track of the inconsistency between those workers. Okay, so the inconsistency means which iteration you are when you try to update the model or communicate to your prompt server, for example. Okay, so as showing here, right, if there's a synchronous communication, then every thread has a synchronous view. So they update the model at the same time. And if it's an asynchronous, then you can see some of the models already doing the second iteration while other workers still computing in the first iteration. And without a bound, the iteration, the difference of iteration among the workers can be keep increasing. So the store synchronous will record which iteration is computing for each worker, and it will make sure the differences is within a certain threshold number. So it's pretty much like marathon competition, right? So some people run very fast, some people very slow. So they are all at a different round in the competition. But you have a bound to say that the slowest one and the fastest one need to be within the distance of 3 rounds. So if it's more than that, the fastest runner need to stop and wait until the slowest one to catch up. So that's what we call the store synchronous. Okay. All right. So this strategy has been supported in many deep learning framework, and you can tune the threshold to strike the balance between, again, the accuracy and the performance. Okay. All right. And the fourth strategy I want to introduce is quantization. So it is a very general approach, and even up to date, many people still try to use this strategy to reduce the computation time for the especially for the forward propagation of deep learning. So this strategy is not just for training; it can also be very helpful for inferencing. So many AI chip design or AI chip, they will use this strategy as well in order to reduce the complexity of their chip or reduce the energy consumption of their chip. Okay? And the quantization strategy, basically, maybe we can see the example to be more clear. So the idea is that originally, every weight we know is a floating point um, data, right? Value. And even if you are half precision, maybe it takes up to by 8 bits, right, to represent that value. So if it's a 1 bit SGD, that means you will quantize this value to just 1 bit. Okay. And the idea is that, for example, it will has a threshold, say 0.23. Okay. If your original value is smaller than this, I will represent by 0. And if it's larger than this threshold, I will represent by 1. Okay. So the value will be either 0 or 1. Okay. So after this quantization, I can reduce the data size by 8 times, right? If originally use 8 bit. And normally we actually use 4 bytes floating point to represent each weight. So if we use 1 bit to replace that, we can greatly reduce the data transfer size by 32 times. So of course it can reduce the communication time, right? Okay. And for AI chip, it's not about communication. It's about the energy consumption of computation. So your computation apply on 4 bytes and 1 bit. Of course, you will, if you can apply on 1 bit, you will save a lot of energy as well. Okay. So quantization is a very effective way to reduce amount of communication and computation. Okay. However, of course, there's an information loss, right? So again, it's a trade-off because again, every iteration you might reduce the communication time of each iteration, but you might require more iterations to reach some training accuracy because of the loss of this information. Okay, and of course, it's not, you cannot just quantize the value arbitrary, right? Every quantization algorithm has a theory or proof behind it to ensure that at least it will still allow the training to converge. Okay, so there is some property behind it. Uh, so um, there are still there are many library you could use to quantize the value. Okay, and usually it's not as simple as what we show over here. This is just a naive example to give you the idea why quantization can reduce communication or computation time. Okay. All right. So this strategy again, you can see from some of the deep learning framework, and one of the example is from CNTK. Okay, the deep learning framework from Microsoft. Uh, you can enable it to use 1-bit SGD for your training. And for other framework, I believe they also probably support their own quantization strategy to improve the training performance. Okay. All right. So finally, we want to let you know that, especially for distributed training, sometimes it's not just about the computing and communication task of your own job, because in a distributed training, usually we will build a cluster to do that, right? So the resource is usually shared by multiple training jobs. So how to place and manage the resources among those training jobs could also affect the performance and the resource utilization. So as shown over here, you can see that say we have each server has 4 GPU, and probably each CPU only connect to 2 GPU. So if you don't place your training task or worker carefully on those GPU or server, you might suffer from a longer network delay, right? In this case, if if your distributed job is or distributed training job is placed on GPU 1 and 2, then when they need to communicate with each other, they have to go through CPU. Okay, so it will be slower, and you will not be able to take advantage of the network, the network bandwidth like NVLink, right? So it will be much slower. Okay. On the other hand, if you are aware of the network topology, and when you dispatch the task and the job, you place those two tasks on the same on the GPU of the same CPU, then they can probably even use peer-to-peer communication to utilize NVLink and reduce your communication delay, right? So you can see the placement will affect the communication time. And this is for a single job. Then how about for multiple job? The problem for multiple job is performance interference and resource contention. So you can see in this case, not only the communication between your workers of the same job will be longer due to the longer the network transfer paths, but also they will have more contention on the network bandwidth between CPU, right? So if you run two jobs, they will fight for the limited bandwidth, and if you have resource contention, that means they will suffer from more performance degradation. On the other hand, if we are aware of this, our scheduler place the first job in the first CPU and the second job in the second CPU, then they will not share the same links. So they will have less performance interference and degradation. Okay, so this become a system-wide problem, right? The scheduler need to properly provision and allocate resources among those distributed job. Okay, and finally, one last problem is resource fragmentation. Okay, so you have fragmentation problem because, like this case, you might have just one GPU left under this CPU socket, or only two GPU left on this server. So if you have a job require maybe 3 GPU, then you don't want to place it on across two nodes because that's even slower, right? So if your resource is very fragmented, then either you have to wait until the resource become available to allow your job to place on a single node, or you have to place it across nodes and suffer from longer network delay. So how to manage those fragmented resource is also a problem. And some of the deep learning cluster, they will even try to migrate the jobs between those GPU or server in order to resolve or mitigate the resource fragmentation problem. Okay? All right. So in principle, of course, due to the network communication overhead, the scheduler will prefer to use packing strategy. But if you enforce this strictly, then sometimes you will suffer from the resource fragmentation problem and suffer from longer queuing delay or waiting time. On the other hand, if you try to spread your worker across GPU or servers, of course you can minimize resource fragmentation, but you will definitely suffer from longer or more communication overhead. So again, it's a trade-off, and it's a decision that need to be made and optimized by the system manager, cluster manager, not just from your single job program. Okay. All right. So to sum up, for distributed training, hopefully now you have idea that aware that there are two pair reason you could use. You could use one is data pair reason, the other is model pair reason. And for data pair reason or for in general for distributed training, there are also many parameters that could affect the communication overhead or performance of your training job. Okay? And so usually the principle is use a larger batch size, right? And also if you use larger batch size, usually you will also increase the learning rate, okay? Because if you use a larger batch size, you will smooth out the, the gradient from all the records, right? So in order to right amplify or to increase the impact again, one strategy is to increase the learning rate. So sometimes you cannot just change the batch size. Usually you will need to change the learning rate according to your batch size, proportional to your batch size. Okay, so those are some general rule you should be aware when using distributed training. Okay, and of course there are synchronous, store synchronous, parameter or reduce different communication strategy, right? So it depends on whether you have a homogeneous environment or heterogeneous environment. And finally, for a cluster, for the scheduler, the cluster scheduler or the resource manager, um, sometimes they have to aware of the behavior of those training jobs in order to have the best resource allocation for the job. Okay, so in order to minimize resource contention and minimize communication overhead. Okay. All right, so you can see this is why it is not very trivial to apply distributed training, because you have to aware all those knowledge about parallel and distributed computing and performance tuning in order to actually achieve better performance than the sequential training. So but it's more complicated, but sometimes you have to use it when your problem size is too large, or you have a time constraint, right? You want to use lower computing efficiency in order to complete your training before the deadline. Okay, so for many cases, especially in large company or for large model training, you have to use distributed training. Okay, so hopefully when one day you have to use it, you already have the knowledge to do it. So we give you a jump start to solving the problem. Okay, all right. So after we introduce those strategy, then we will quickly to show how those strategy are actually used or provided by the real deep learning framework like TensorFlow and Horovod. So um, how can you use them from the tool that can be accessed by you, right? Okay, so first of all, right, distributed training sometimes is a necessary solution. So you can see there are many solutions provide distributed training. Okay, so we quickly summarize it over here, and you can quickly check out whether they support model pair reason or data pair reason, whether they support GPU, and if you are interested to use them, some of them have open source. So you can also read their documents. Okay, all right. So of course, however, the one of the most popular deep learning framework is TensorFlow, right? I think everyone knows it. It's developed by Google, right? So many people use it to develop their deep learning model and deploy their deep learning solution. Okay, so we use TensorFlow as example to let you know how it provides distributed training. Okay, so first of all, TensorFlow has a very modularized structure, okay, code structure. And as a matter of fact, the core of TensorFlow is actually implemented in C. Okay. However, you use Python to do the TensorFlow coding is just because it provides the interface in Python. Okay, so it's easier for programmer to use, right? But the core engine is actually a DAG scheduler. Okay, pretty much again like the execution we introduced in Spark and MapReduce. Basically, it's a execution engine that can convert the DAG you described from your Python code to a set of computing tasks and data flow that will execute it on the computing device. And you can see a very important system design idea from TensorFlow is they want to allow the computation on any computing devices. So the computing task eventually become what we call the operator. So each of computing task is an independent computing task called operator. And operator can be implemented in different languages depending on the computing device, like the CUDA version or the CPU version. So depending on where you want to run the operator, they will issue the operator. They will use the different implementation of the operator to perform the computation. Okay, so that's why TensorFlow is portable, okay, across hardware platforms. Okay, and for us, of course, we the distributed training happens in the execution engine, right? When he try to just like OpenMP or other tools that can automatically, right, convert your sequential code to a parallel code. Okay, so that's actually happened within the execution engine. Okay, right. It's a bit more detailed, but we just briefly introduce it. And with the knowledge you have learned from this course and with your experience from your final homework for implementing the MapReduce framework by yourself, I think you can kind of imagine, understand how TensorFlow can generate distributed computing tasks for your neural network model. Okay, and basically, TensorFlow itself, in order to support distributed training, it also has its own master and worker. Okay, and worker simply are the server or process right, that will perform the computation of those operator. And the master is acting like the scheduler or planner that will dispatch those operator computing tasks to the worker. Okay. So what happened is that, for example, this is your TensorFlow Python code, right? And as you know, this is supposedly to describe a neural network graph. And the graph, as we said, is basically a deck, right? And so for the execution engine, what happened is he will try to partition the deck, okay, or generate the deck for distributed training. And because those training tasks can be run across workers, machines, so you will also insert some of the data transfer operator to your deck. Okay, and so this is how they will try to convert it to into a distributed training job. Okay, so you can see this is example that if you are using the parameter server strategy to do distributed training, then that means there are some processes or worker that will act like a parameter server, and other process work as a worker. And if the data, the tensor or the weight need to transfer from worker to parameter server, then the execution engine will do the planning and insert the send and receive operator or operator to their computing tasks, so they can connect to each other. Okay. All right. So basically, this is done automatically in the execution engine because you always follow this strategy to parallelize your your training job, right? All right. So basically, that's exactly what happens. So after you do that, then basically, although they have two worker, but this worker probably is the our training worker, right? And this worker, as you can see, says PS. So this is a parameter server. Okay. So the term worker here referring to the role of inside the job. On the other hand, the worker here referring to the server in this distributed platform. Okay, so don't get mistake that the parameter server, it must be a worker. Okay, so actually parameter server is not run on master. Parameter server is just a user task that will run on the worker as well. Okay. All right. So this is how TensorFlow will dispatch, partition, and dispatch those tasks around the worker. And all the planning has been done in advance, and the computing order is controlled by the master. Okay. All right. So okay, so that's what's under the hood in short. Okay, and for a user, if you want to use distributed training in TensorFlow, you will see that you actually need to describe. You have to describe a cluster spec, so that the TensorFlow executing engine will know how to create the role of their master and worker, etc. Okay. So to do that, you have to have this define this spec and to create the role we just mentioned, and the rest will be done by the execution engine to decide what task will be send it to which worker. Okay, all right, and so all those are detailed. So as a user, besides to specify this cluster spec to know what are the server will take part in this distributed training. Besides that, you have to um, use the API, right, to tell the TensorFlow to train your model in a distributed fashion. So the easiest way to do that is through the estimator API provided by TensorFlow. So estimator is an even higher level of API defined by TensorFlow. So of course it's a Python code, but it's even higher level of API interface for user. So in this layer, it defines those distributed method. So all you need to do is to code the API for distributed training and choose the strategy you want to use. And with the cluster spec you provide, then the TensorFlow engine will know how to generate the DAG we mentioned, and it will manage the computing for you. Okay. All right. So I think we will show the code in the lab. Okay. So in the lab slides, you will definitely see this. You are in the step-by-step instruction. You will use those API, and all you need to do is to just add a few lines of code in your Python code. Okay. This a bit of detail, but we have told you that for training, you can do synchronous training or asynchronous training, right? So for TensorFlow, you can do that as well. But it's a bit more complicated. If you someday, if you're really interested in this, you can just Google it to know how to modify your training code to do the synchronous or asynchronous training. Okay. By default, actually, I remember it's actually a asynchronous training. So synchronous training is actually a bit more complicated. Okay. I think we'll skip this part. This is really too detailed. It's more about the detailed implementation of how the DAG is managed by TensorFlow. In short, in the past, in the older version, what they did is because every task have to every worker is not aware the existence of other worker. So they all thought they are the only one try to train this model, but actually TensorFlow um, doesn't allow them just to prevent this too complicated. So actually they use other technique to exchange the data between those workers. So it will generate a deck that's very, very huge with redundant graph partition or subgraph for each of the worker. It simply just, you have to, in order to do distributed training, he has to replicate the graph multiple times. Okay, and then partition again, assigned to each worker. So as a result, the master will consume too much memory, in short. So the new implementation is that you don't need to duplicate the graph for every worker, in short. So it's more scalable. Okay. Um, so if you look at the code, if you wonder why there could be different way um, to modify your code for distributed training, that's probably because you try to use them differently. Okay. You don't need to worry about this because if you use the estimator, then the estimator will handle those details for you. Okay, so that's why it's better to use a higher level API. If you use a lower level API, you have to write the code we show over here. So it's more complicated anyway. Okay. All right. So this is just a reference. So I don't think you need to look into it too much. Okay. Okay. So today, actually, more people use Horrible for distributed training than all other methods, I believe. And the reason is Horrible is a more general interface or a thin layer for specific for distributed training. And you can see that the Horrible can connect it to many training frameworks, including the most popular TensorFlow and PyTorch, etc. And the reason is because it follows the data parallelism method. And as we already introduced to you, that with this method, all you need is to implement a O-reduce function at the end of the forward propagation, right? So it's actually not affected by how you do the forwarding or backwarding computation, or how you how you what interface or API you use to develop the neural network model. The computation and the communication can be separated. So that's why we can use Horrible to connect different worker or process for local training, and together become a distributed training behavior. Okay. All right. And as a matter of fact, Horrible, at least at initially, today still supported using MPI. Okay, so Horrible actually is an MPI program, and it used MPI to launch those processes and to code the TensorFlow library to perform local training, and use MPI to, especially the O-reduce API in MPI, to do the parameter swapping. Actually, it's not too far from what you have been implemented or you have learned from this course. Okay, and we have also mentioned, right, especially for GPU, it provides its own library for collective communication, like Nico. So Horrible, in order to optimize its performance, it could also leverage a library like Nico to accelerate its communication methods, like the old reduce function. Okay, then it can also, because it's MPI, naturally it can support infinite band, right? Those RDMA networking. So it will be it can fully utilize those HPC technologies, basically. Okay. And by the way, the name of the Horribles comes from the Russian folk dance. So you probably seen from television. So it's people that uh, become a circle, and they hand to hand to each other and do the dancing. So it's just like the behavior of Horrible. And because Horrible, the method, the communication implemented by Horrible is the ring or reduce method we talked about. So here has a step by step process for ring or reduce. But basically, as we mentioned before, um, imagine this is the parameters or the new gradient or new weight generated by each worker independently, and our goal is to eventually, right, collect the weight from all the models and compute the sum, then take the average, become the new weight for the for the model in the next round. Okay, so for ring or reduce, you can see try to explore the pairwise communication bandwidth. So every step, you will try to propagate one part of its value to the next process. Okay, and the one receive that value will just do the prefix or the partial sum, right? And then send out the partial sum to the next uh, next process again. And you only send one part because remember you don't want to have race condition, right? So basically, if you have three people, right, three process or three worker in this computation, then we will partition the parameter into three part and do the sending and computing of one part per worker. So that's the idea. So at the end, you will see you can after basically n rounds, you will get the result of O reduce. Okay, And although, of course, after after n rounds, you have to do the average. So that's the total. You have to do n minus one send and receive, and do n minus one adding. Okay, um, because this is just propagate to do the sum, and then you have to um, basically take the average. Okay. So anyway, it may seems like it takes more iterations, but actually it could still be faster because you won't suffer from any hard links. So you won't suffer from network congestion problem. So the aggregate bandwidth in the cluster will be much more than the bandwidth of a single link. So that's why Horrible is suitable for high bandwidth, high throughput communication. Okay. All right. It's actually not the best one. If you look at the recent research, there are a lot more variants of ring reduce that could further optimize the result or the performance on a variety of network topologies. Okay. And as a matter of fact, a library like Nickel, he will detect the network topology and to choose what would be the best implementation for all reduce API. So that's why you can try to achieve the better performance. Okay. All right. So without any surprise, with Horrible, if you compare to the distributed TensorFlow method based on parameter server, a centralized communication method, Horrible can achieve better performance because it's a peer-to-peer communication, and also because it can take advantage the high bandwidth, low latency of infinite band, while TensorFlow is implemented based on remote procedure code, which can only run on socket programming. So it's not suitable for infinite band. Okay. Um, so basically, Horrible can achieve better performance than um, the version we have from from TensorFlow. So people like to use Horrible more than others, and you can use it on any frameworks as well, right? So it has better portability. Okay. All right. So finally, we reached the last part of this lecture and our course. So here we give you a brief overview about more knowledge and trend on how to apply parallel computing for deep learning. And so, so first of all, like the content we introduced in this lecture, we are tackling the deep learning problem from a different aspect, as we said. We are tackling the deep learning problem from the computing side, right? So, as a matter of fact, there are a lot more than just design or implement the deep learning model. And as a matter of fact, people already realize that for real AI or machine learning solution, only 5% of the production code is about the machine learning model, the model design itself. All the other 95% of code is try to provide the environment and the system to support the whole solution. Okay, so that including, for example, how can you collect data, right? And after you have the data, how can you verify the data? How you clean up the data? How you do feature extraction? And then when you try to train the model, you have to probably use distributed training. Then, as we introduce, it's also about how you manage your computing resources, right? And so you have to monitor the training, monitor the computing performance, and in order to optimize the training time, right? And after you do the training, you probably still need some analysis tool to know how you want to retrain the model in order to get a better results. And after you done the training, the training is done, you have to deploy the model, become a real AI solution. So you might involve edge computing, you might involve service and operations, right? In order to have to ensure the solution is really usable, right? So in short, it's not just about the algorithm, not just the model. You need a system to run the algorithm, right? And you have to maintain this solution and and perform the end-to-end machine learning process, hopefully in an automatic manner, okay, with as little human involvement or intervention as possible. So you have to solve many problems. Okay, so in order to tackle those problems, we now already have a new form community called the machine learning system. Okay, so this community is the mission of this community is to develop and solve all those problems in order to make uh, a, a AI or ML solution become a production code. Okay, that's the actually the challenge we are facing now in the industry, because you can probably find many very good model from the open source community, right? And assuming you have enough data, then it's actually not hard to train those model and to use them. But in fact, it's still very hard to make it become a production code because of all the issue we mentioned before. And to solve that, um, it's more about how you build a system, how you manage the data and the computation in the system in order to support this algorithm or this solution. Okay. So as you can see, right, the machine learning system involve many issues, involve basically everything that required to support the machine learning model become a production code in the real world. And because right now many products or many solutions are provided as the form of a service, right? Probably on cloud. So this production system is no it it's a no it's keep running, right? It should be a continuous delivering service. So it also involves how you operate and manage the service. So many of you probably heard about DevOps, right? Idea of that you want to consider operation and development at the same time. So for machine learning, it's similar. The similar concept become what we call the ML ops. Okay, so the idea is same thing. How you can combine the developing phase and the operation phase of a machine learning solution. And it could even be more complicated because the machine learning process involve a lot more things, right? You have from how to collect data, to analyze the data, to tune the model, etc. There are many new challenges. Okay, all right. So as I said, no, this is a new community, and there are many issues waiting to be solved, and it's necessary because most of the time those issues involve how to perform those actions in a distributed and parallel fashion on a cluster. Because machine learning itself or deep learning itself is driven by computing power and data. So all those solutions usually runs on a cluster or on a on a cloud environment. So you will need to face those distributed and parallel computing problem. And of course, not all the user, especially those data scientists or AI scientists, uh, they don't know much about this side of the problem, right? So that's why we need to build those systems to hide those complicated problems from the user, so they can easily develop or focused on their machine learning model, while the machine learning systems can handle the rest of the 95% of the code. Okay, so you can imagine this is a field that far from being mature. So there are great demand to design and implement those ML systems and ML systems solutions. Okay, so just take a few examples like the distributed training we introduce is part of this field, right? So how can we um, generate the code for the user, right? How can we optimize the communication performance of a distributed training or inference? And for AI chip, it's also a very hot topic. So same thing, how can we design an AI chip with lower energy consumption and lower probably latency delay, right? So how can design this, how to do this chip design, okay? Or the machine learning is usually we call it a machine learning pipeline. So you have many stage of operation you need to perform, from collecting data to training data to deploy the inference services. So how can you manage the life cycle, like the problem we face in ML ops? Okay, so there are many issues that arise because of the need for machine learning. Okay, all right. So so it's a big field. We try to just let you know some of the issues. So we already talked about distributed training. So the next thing I want to introduce is the problem for auto ML, right? So as I said, for machine learning, usually we characterize the whole process as a machine learning workflow or ML workflow, because you have many stages, right, for doing different things. Okay, and each of stage, of course, is a challenge, but usually you have to to get the best result you can get from each stage before you move on to the next stage. Because, for example, like deep learning model, we all know um, it's a its result, it depends on the input, right? If you give him, if the input is garbage, the output is garbage. So how you get the correct input depending on how you do the data pre-processing beforehand, right? So there are many, every stage in the workflow is important. And every stage usually involve many parameter tuning, right? All those parameters are considered to be those hyperparameter, okay? So if you want to, so it's a large search space. So usually it's hard to do that manually, right? Either you require infinite amount of time and computing resources to search through the problem space, or you are an expert, so you have the experience, you have the skills, unique skills to quickly identify or search the problem space. Okay, um, so the first solution usually don't work because that you don't have that much time and money to do that. The second solution also very costly, but mostly is what we relying on right now. So we have to work with expert, right? People with domain knowledge to develop or tune the model. But the experts are very expensive, and they don't want to spend time on just to tune your model. So that's why we want to have a we have this problem called auto ML. Basically, we try to automate the whole process without the human intervention. So so we can do this automatically and hopefully smartly, right? So for the developer, the end goal is that they only need to collect the data and define what they want to predict, and then everything can be done automatically by some systems or algorithm to automate the whole process and to get us the best result. Okay. Okay. So how can we do that? Of course, it requires a lot of techniques, right? And just as example, one of the problem in AutoML is the hyperparameter tuning problem. So this problem is focusing on the model training step. And for example, we said in model training, you need to choose the right learning rate, right? The dropout ratio or the number of layers. Okay, those parameters or batch size, right? So you have hundreds of parameters, and you want to know which setting can lead you the best training results. So it's basically a search problem. Okay, and there are some ways to do that, some algorithms for for searching, right? For example, grid search is try to basically um, you know uh, partition or you have for example, maybe your tuning range is from 1 to 10, and he will test 2, 4, 6, 8, and then 10. So you have a regular way to test all the tests around the space. So that's why you can see each dot here represent some sampling point. And a method like research will try to evenly scatter his sampling point, test point across the search space and try to find maybe the position that lead to the red color, right? Okay, and random search is just randomly scattered around the space. And adaptive selections method is the one that will adaptively decide which position you try to sample depending on the result from the previous iteration. So similar to gradient descent, right? It's kind of it's depending on the previous result to decide how to adjust his weight. Similar thing. So this is a class of algorithm that has adaptive can adapt to the training process or the tuning process. Okay. All right. So well, this is not the focus of our course. So this is more related to algorithm and more about the math itself. And just let you know that one of the famous methods called the Bayesian optimization. So this is the one that belongs to the adaptive selection algorithm. And so that's why you can imagine it's probably can lead you to the best result with earlier, right? With less, with fewer number of iterations. Okay. But sometimes it's not just about the math. Okay, so this is the problem you want to solve. You need to solve if you try to do the tuning on a single core, a single machine, because usually you can only evaluate one trial or one result at a time, right? Especially for Bayesian optimization. But in practice, again, maybe you want to do the tuning on multiple machines. So if you have multiple machines, that could also affect how you tune the parameter. And if you want to tune the parameter on multiple machine, it's called the massively parallel hyperparameter problem. Okay, the key of this problem is that the advantage of this problem is that because you have so many machines, so a way to do that is you can launch multiple trials at the same time, right? You can run one trial on one machine. So after a certain epochs or time, you can compare the result of those trials and filter out the trials that give you worse results in just after a certain epochs or iteration. You don't need to train the model to the end, right? Because you can use comparison to know whether the curve for your accuracy, whether it's keep growing, or it's already stopped, or it's much worse than others. By comparing all the trials at the same time, you can early stop the training for the bad trials. So that's why you can filter out the result more quickly than the previous method when you only have one core, right? If you have only one core, usually people will train the model to the end to get the result. But if you have multiple machine, you can train those trials at the same time. Then you can use early stop to more quickly get a better results. Okay. All right. So this is the idea, the common strategy for parallel hyperparameter tuning, and the most famous one is called the successive halfling. So its idea is that after a certain epoch, it will filter out a certain ratio of the result. You can control that ratio. Maybe it's one half or maybe it's one third. You can choose that to see how aggressive you want to filter out the result. You don't want to do that too aggressively, because sometimes the learning curve, right? It's curve usually is not smoothly increased, right? Some trials maybe increase slower at the beginning, but maybe increase much faster at the end. So you have a risk if you want to terminate early. Okay, so that's why still involves some tuning, but in general, it can be more efficient. Okay, all right. So um, so that's hyperparameter tuning. You can see there are also quite a few problems that they are waiting for better solution. Okay, and the next part is we want to just briefly cover, right, the issue, especially the performance or computing issue for either training or inference at the data center side or at the edge side. Okay, so you can see for deep learning, usually it consists of the training phase and inference phase, right? And for each phase, it can be done in a centralized computing environment like cloud, HPC, or data center, or it can be done distributedly across scatter around on those edge or embedded device. Okay, and so um, the behavior of the computation are different between training and inference, and the computing capability between centralized and decentralized are also different. So you might face different challenges as well. Okay, so for example, if you do the training on data center, usually you will use GPU, right? But if you are doing training on the edge device, then you might require other training method that require fewer amount of less amount of communication, because across edge the network is not stable and its bandwidth is limited. And also you might have some data privacy issue, because um, the data on those edge usually belongs to different user, so they don't want to expose their data um, during training. So that's why federated learning has been proposed, and it is one of the hot topic in recent days. So we will briefly mention it as well. Okay, and for inferencing, if it's on data center, you might use those ASIC chip like the Tensor Core we mentioned. And on embedded device, you will not only on a Tensor Core, sometimes you will use ASIC AI chip, so you can further reduce the power, and it's a specific design on a certain edge device. Okay, all right. So um, so for deep learning, you can see it's a more complicated problem if you look at the end-to-end life cycle from data collection to model inferencing. And in fact, most no, most of the time, the solution we try to provide involve both edge and the cloud, right? For example, you will try to collect the data at the edge side, and the data probably will collect it to a centralized data repository in cloud. But the network bandwidth between edge and cloud is limited, so you might need to extract features and filter some data, do some data preprocessing at the edge location as well. And the cloud has sufficient resources for you to do distributed training. And but after the training result, uh, after you do the training, the trained model needs to again deploy on the edge device in order to allow the user to access it, right? And also to inference the model, you will probably use the data that some runtime collected data to do the inferencing. So the end-to-end machine learning life cycle or the system solution sometimes it's even across different computing environment. So that's why sometimes there are many new challenges. Okay, so some of the interesting solution, for example, like for inferencing, because we have this cloud and edge infrastructure. So no, couple years ago already, you can see 5 years ago, people proposed this branch net solution, which will provide some early exit point in his neural network model. So unlike the traditional neural network model, we only get the result from the last layer. This new network provide other exit point. So if the feature is very easy to identify, he might return the result earlier. And if it's more complicated, you might need to wait until the last layer. Okay. And this model, if you apply to the cloud and edge environment, you can choose to deploy the first layer on the edge device and the later layers in the cloud device, in the cloud system, okay, or cloud platform, so that the later layers can be more complicated and more resource consuming, but the earlier layer can be less resource consuming, so it can fit to the edge device. Okay, so this is some of the example that you have to customize your model according to the computing environment and leverage the advantage or the strengths of different computing environment. Okay. All right, and for AI chip, the example we show you is called this CS1. Okay, so CS1 is a AI chip. It's more than an AI chip. It's actually a no, it's a processor for AI. And what's different is this processor. You can see the processor chip itself is very huge. Usually, a chip is very small, right? Probably smaller than one centimeter, right? But this chip you can see is well maybe 10 or 20 centimeter, so it's much larger. And the reason it needs to be so large is because it can fit in more cores on the chip, so it can provide even more computing power than GPU. Okay, but it's not easy to produce this kind of chip because we all know during manufacturing you have those fail rate, right? So if the area is larger, the fail rate is much higher. It grows in exponential. So as a matter of fact, this kind of chip usually cannot guarantee there's no failure. Okay, so the software on top of it need to be specially designed to be able to tolerate those values. So it's entirely new problem and solutions. Okay. But anyway, this has been proposed in 3 years ago. It's a very new idea and a very new product. And if you are interested in this, you can Google it and see how it has been developed in recent year. Um, but um, but as I know, probably it's not very popular yet. Okay, but this already become a product. Okay, and so people are still try to experience with it, and hopefully it could be some useful solution or cost-effective solution in the future as well. Okay. All right, and so that's for training, but for inference, you know, like the PDU or the tensor core, those are the classic example for AI chip, right? So we have mentioned the idea of AI chip is you will customize the hardware logic for a certain computations, like certain convolution operation or certain neural network model. So that's why it can have better performance and lower energy consumption. And most of them are based on ASIC chip design or like FPGA. Okay, and but the main issue for that is the two issues people are trying to overcome. One is the memory wall problem. So basically, with those chip design, you can easily increase the computing capability and power, but you still need to fit in the data. So the problem becomes the data bandwidth, the data access bandwidth. So so we all know the data is stored in memory. So the memory referring to the problem that we cannot provide enough bandwidth to load the data from memory to those AI chip. So there are two solutions now. One is to use some like 3D memory stack technology, right, to improve the latency and the bandwidth of your memory. The the other direction is try to develop those memory that already have the capability for computing. Of course, it's not general computing, but people already found that it's possible to have the convolution operation on those memory cell. Simply do the multiplication and then do the addition. It is possible to do that on the memory chip. So that means when you read or store data to this memory cell, you can perform the computing in this data path. So this is what we call the processing in memory. So of course, this still not very mature yet, but theoretically it could work. Okay. And the second problem is the software tool chain, right? So you can imagine there are many new AI chip is designed recently, but they have different hardware architecture. So you might require different software stack on top of it for developing, debugging, profiling, etc. So without the proper software environment and software tool chain, it's very difficult and time consuming to develop a solution and deploy a solution to those AI chip. Okay, so those are the big problem we are facing today. Okay. All right, so we just have a few slides left, but we are running out of time, so I will leave it to our lecture on on Thursday, okay? And that will also be our last lecture for the course this semester, okay? So we'll wrap up our course next on Thursday, okay? And don't forget we have the lab on Thursday night as well.